Hey everyone, I wanted to make a video discussing discussion worksheet 8 because I think it's really important and it'll it just covers material that I think can be a little bit tricky the first time you look at it. So hopefully this will be helpful for you guys. So I'll just go through each problem step by step and I'll explain my reasoning and any sort of misconceptions or questions that I think might arise. So let's begin. So here in problem 1, we're essentially told that we have the solenoid over here. I have to remember that you can't see my hands. So we have the solenoid over here. And we essentially want to figure out what happens to this loop of wire that's completely disconnected. So there's like no battery on it. It's completely neutral. We want to see what happens to it when we connect this battery to the solenoid. So essentially what will happen is when we connect this switch over here, current will start flowing through the solenoid. Specifically, it'll start flowing around this way. And so if you curl your fingers in that anti-clockwise direction, again, this way, then your thumb should be pointing this way. Hopefully that's clear. It's kind of hard to sort of draw here on the iPad, but hopefully you can see that. That's really important. And what that means is that the magnetic field from the solenoid is generally going to be pointing to the right, like this. But this is not a perfect solenoid. It's not infinite in length, and overall it's just not perfect. What that means is that there's going to be a magnetic field outside of the solenoid, and it's going to look something like this. It's going to look kind of like a dipole. So you can imagine that I'll draw like a line like this, and a line like this, where the magnetic field goes like this. But if I keep drawing like bigger lines, eventually I'll get a line that goes like this, right? And we can see that it'll enter the wire loop sort of to the right, if that makes sense. So hopefully you can see that the magnetic field inside the loop will go from no magnetic field, because the current was initially 0, to some magnetic field. So there'll be an increasing magnetic field, specifically to the right. Great. So if we can see that, then what we can think about is part A, which asks us what direction the magnetic moment of the loop will point in. So the way to think about this is using Faraday's law, which states that an EMF will be generated such that, it will be equal to the negative derivative of the magnetic flux. And in this problem specifically, we're just going to think about this in a more conceptual way. And so what I want to highlight here is, imagine that, this is me. I'm going to give myself some hair. And I'm looking at this loop from back here. So if I look at the loop from that perspective, let's see that this is what I'm seeing. Originally, there's no magnetic field because there's no current. But when I connect the circuit, when I close the circuit, or when I close the switch, suddenly a magnetic field will be applied. And we will go from no magnetic field to some magnetic field. These lines will be pointing into the page, or in terms of the diagram, to the right. So we can see that we've had this change. Again, this is really important to illustrate. We go from no magnetic field to some magnetic field. This means that our magnetic flux is increasing, because in general, the magnetic flux is equal to the magnetic field times the area of the loop. So if the magnetic flux increases, that means that we have an EMF generated, because our time rate of change of the magnetic flux is going to be non-zero. Again, there is a changing magnetic flux. And so what we have to figure out now is what direction of current will generate the appropriate magnetic moment. In other words, we know that we go from no magnetic field to some magnetic field. The loop is going to want to oppose this. It doesn't like this change in flux. And so it'll point in the opposite direction. So you can imagine these magnetic field lines sort of pointing out of the page, opposing this change in magnetic field. And for that to be the case, we can think of this in terms of another right-hand rule. We can point our thumb in the direction of, out of the page, and curl our fingers. And this is going to give us this counterclockwise current. Again, point your thumb out of the page and then curl your fingers. So what this means is, if we think about this in terms of this diagram over here, the magnetic moment is going to point this way. This will be our mu. And so the correct answer is pointing to the left for the reasons that I just explained. So hopefully that's clear. This is a really important way to approach this. So now let's consider part B. A long time after the switch has been closed, the wire loop has a magnetic moment, and then we have to figure out where it's pointing. So after a long time, the solenoid is no longer going to essentially resist the current. And we'll learn more about this soon. But essentially, after a long time, the magnetic field in the current in the solenoid is going to stay constant, and the magnetic field going through the loop of wire is going to be constant. In other words, if we erase this over here, I'll just draw a new circle. So after a long time, what we'll get is the magnetic field going into the loop is just not going to change anymore. If it doesn't change anymore, that means that our rate of change of the flux is going to be 0, because the flux is just staying the same. Again, the area is staying the same, the magnetic field is not changing, so our rate of change is 0, which means that there will be no magnetic moment in the loop. I hope this makes sense. Again, you have to think about how the magnetic flux changes. So hopefully that's okay. So now let's consider what happens after we have reopened the switch. So you can imagine that when we reopen the switch, no more current will be flowing in the solenoid, and what will happen is the magnetic field will go to 0. In other words, we'll have a drop in magnetic field. So again, let's picture what we had before. So initially, we had no magnetic field. Then when we connected the circuit, we started to have some magnetic field lines going into the page. And now what we've been told is suddenly by disconnecting the circuit, we're going to lose this magnetic field. It'll all go to 0. And so the loop doesn't like this, right? It's going to oppose this change in flux. So again, it's going from magnetic field pointing in to losing some of it. So to oppose this decreasing magnetic flux, it's going to point its magnetic moment into the page to sort of reinforce this original flux. Again, this is extremely important to understand, so I hope this is crystal clear. We started with a bunch of magnetic field going into the page. When we disconnect the circuit, our magnetic field is going to start to decrease. To oppose this decrease, the magnetic moment is going to be pointing in such a way where we reinforce the original magnetic field. And so the question is, where does the current point such that this is the case? Well, what we're going to do is we're just going to point our thumb into the page in the direction of the magnetic moment and then curl our fingers, and this will give us a clockwise current. So if we think about it in terms of the diagram, our magnetic moment is pointing to the right, so this is the right answer. Hopefully that's clear. Finally, we're told that to think about what happens after a long time. After a long time of the current being disconnected, we can imagine that the magnetic field will just be 0, and it will no longer be changing. It'll just be 0 forever. And so that means that this will just go down to 0. There won't be any more current, so I'll just try to erase these arrows. And since there is no change in flux, again, from Faraday's law over here, there will be no current in the loop, which means that there will be no magnetic moment. Again, it's the current in the loop that generates this moment. In other words, no magnetic moment. So hopefully that's clear. I think if you can do this problem and sort of explain this reasoning by yourself, I think that puts you in a really good position in terms of understanding Faraday's law conceptually. So now let's move on to problem 2, which is a little bit more mathematical. And I think if you're able to do this sort of problem, you'll have a very good sort of fundamental understanding of how to approach any other problem like this. So let's consider what's going on here. We have this infinitely long wire, and it has current going up. And importantly, and this is very different from our previous problems, we have a time dependence on our current. So that will be something that's important to keep in mind. We also have a square loop out there in space, and we know a few distances in the problem, so this will be something to keep in mind. So let's just go into this and see what we are being asked. So in part A, we have to figure out an expression for the magnetic field as a function of the distance r that we are away from this wire. Okay, so the way we can figure this out is by using Ampere's law. So let's begin by imagining or by visualizing what the magnetic field looks like. So the way you can do this is by pointing your thumb in the direction of the current, so up, and then curling your fingers. And you can see that you'll get something that looks like this. That's a circle. Okay, so we're going to get something that looks like this. It's going to be pointing into the page on the right-hand side and out of the page on the left-hand side. Again, magnetic fields curl around currents, and that's really, really important. So since we're only concerned with the magnetic field on this side of the system, we can just say that's going to be into the page. Okay, so now that we know the direction of the magnetic field over here, it's going to be into the page. Let's actually figure out the expression, and we're going to do this using Ampere's law. And so Ampere's law says that the line integral of B dot dl is equal to mu naught times the current enclosed. Great. Again, I'm going to draw again our magnetic field, or at least one magnetic field line. And here is something that's really important. Our Amperian loop is going to be one where we walk along this exact magnetic field line. And the reason why this works is because the magnetic field has constant strength at each point in this circle, because they're all a distance r away, because it's just a circle. And so this allows us to compute this line integral in a really easy way. And so what we can get is that the magnetic field is equal to B, or well, we're going to get B times the radius or the circumference of our path, which is 2 pi r, because it's a circle. And that's going to be equal to mu naught and the current enclosed. In this case, the current enclosed is going to be I. But remember, I is a function of t. And so we're just going to replace I enclosed with I of t. We can now solve for the magnetic field. We're going to get mu naught I of t. Again, let's emphasize that it's a function of time times 2 pi r. And if we want to be consistent, we can also label that it goes into the page. I don't think we've been given a coordinate system in this problem, so let's just say that up is the z direction, to the right is the y direction, and out of the page is the x direction. And so we can see that if the magnetic field is going into the page, we're going to have a negative I hat vector. And so now this becomes a vector. And this is our magnetic field. So here's something that's really important to understand conceptually. We can see that we have both a position and time dependence. And so let's just say we consider like some arbitrary position, like over here. If the current is changing, then our magnetic field value is going to change over time. So if the current is increasing, our magnetic field is going to increase in strength. And if it's decreasing, it's going to decrease in strength. And as you can imagine, since the flux depends on the area and the magnetic field, if we have a time-dependent magnetic field, our flux is obviously going to change. And we're going to see this throughout the problem. But hopefully you can see that this is the case. All right, so for part B, we're asked if we can use this expression, the flux being equal to B times A, and the answer is no. And the reason is because B times A is sort of like a special case of the general expression for flux. So the way I like to think about it is that flux, I have a pretty bad memory, and so I like to just remember like the very basic definitions and then try to derive whatever other special cases from those. And so what I remember is that the flux is defined as B dot dA. And so you can imagine that if the magnetic field is a constant throughout our surface, then we can just pull it out, and we'll just have the integral of dA. And this will just be equal to B times A, which reduces down to this nice expression. But in this case, our magnetic field is not constant throughout the surface. We can see that if I pick out like this like region of surface, and this one over here is closer to the wire compared to this one. And so the magnetic field through this part is going to be stronger than over here. And that means that they're going to have different magnetic field strengths, which means that when I integrate over this surface to find the total flux, I can't assume that they have the same magnetic field. So I'm actually going to have to do a proper integral. So that's why we can't use B times A. And in fact, we can only use this expression. So hopefully this also illuminates like, where this comes from. Cool. So now we are told to pretty much do just that. So we're told that we have these two strips in our surface, and we want to compare what the magnetic flux is through there. So let's consider strip 1. So strip 1 is closer to the wire than strip 2, which is clearly further away. And since they both have the same time dependence, in other words, the magnetic field will evolve at the same rate. We don't have to think of any relativistic things, so don't worry about that. We can just say that the magnetic field through this is going to be stronger than this one, and they both have the same area. They both have an area of dA is equal to h, the height, times the base, dr, because they both have height h and base dr. And so, since the area is going to be the same, but the magnetic field for this one is going to be stronger, we can say that this one over here, number 1, is going to have more flux. So in other words, number 1 has more flux than number 2. Hopefully that's clear. Okay, so now we want to write an expression for the infinitesimal amount of flux going through a given section of the loop. And this can seem a little bit weird, at least mathematically. What we're essentially saying is we're going to, to do this integral over the surface, we're going to break it apart into a bunch of little sections. Because this will allow us to add them up and to compute the total flux. So to be super clear, what we're essentially doing is we're saying the total amount of flux through that surface is equal to the integral of all the little pieces of flux. Again, we're asked to find what the flux of B is. And so when we add them up in an integral, that's what we get. And this is exactly equal to our previous definition where we had B dot dA. In other words, a little bit of flux through a small area is equal to B, the magnetic field through that area, dotted with the area vector. In this case, we can say that the area vector and the magnetic field are parallel to each other. And so we can actually get rid of the dot product here and the vectors. And so we just get B times dA. Great. So now we just have to replace B with what we know. We know that B is equal to mu naught I of t. Again, it's a function of time over 2 pi r. And we know dA is equal to the height of each very thin rectangle times the base, dr. So now we just plug and chug. So we just put our magnetic field, mu naught I of t, over 2 pi r, times our dA, which is just h dr. And that's the answer. So hopefully that's clear. And so now using this answer over here, we want to find the total flux, which just means calculate this integral over here. So we're going to write our flux here, our integral, and I'm just going to plug in our expression. So mu naught I of t over 2 pi r times h dr. And we can see that this tells us that we're doing an integral over distance, right? Where r represents the cylindrical distance from the wire. And so now we have to ask ourselves, what are the bounds of this integral? And remember, the way we tell the integral, like what shape we're dealing with, is through the bounds. So we have to be very precise with this. So, for example, if we set the lower bound equal to 0, we would be saying that this loop starts at 0, which is incorrect. So let's consider where it starts from. Well, we can see that the leftmost coordinate of this loop is a distance d away. And we can see, and this is a little bit more subtle, the rightmost distance is going to be d plus b, because it's going to be this distance plus this distance. And so hopefully it's clear that our bounds for the integral are going to be d to d plus b. And now we have everything we need. So if you want, we can pull out the constants. So mu naught is a constant, I of t is a constant, and you might be saying like, wait, I thought we were saying that the current was time dependent, right? How can it be a constant? It's constant in terms of position. It doesn't have a position dependence. So we can pull it out in that sense. Great. 2 pi is a constant, and the height is a constant. And so now we just have the integral of 1 over r times dr from d to d plus b. And this is just an integral which is equal to the natural log. So I'm just going to rewrite these constants. And so 2 pi h. And now we just have to evaluate ln r. So I'll write this like this, from d to d plus b. And we can just plug this in, and using a log rule, we can see that this will be equal to, let me just write it out, the natural log of d plus b over d. And that's our answer. That is the total flux in the system. And we can see, and this is really important, the flux is still dependent on time. So as the current increases, if it were to increase, we will be gaining, there will be an increase in flux. If the current was decreasing, we would have a decrease in flux. And so the natural question is, if we are given an expression for the current, like this one, what is going to be the EMF in the loop? So let's do that. So I'm just going to rewrite our expression. So our flux was equal to mu naught over 2 pi. And this time I'm going to write the I of t at the very end. So I'm just going to write all the constants over here. Again, note that ln of d plus b is just a constant. These are just numbers. And now I'll write the current at the very end. So normally we would have I of t, but now we're told that I of t is specifically equal to some constant current, some initial current, times e to the minus at. So we can finally see where the explicit time dependence is. So now I'm just going to plug this in. Oops. I'm going to plug this in here. I naught e to the minus at. And finally, we have an explicit time dependence. So if you want, you can write our flux as being time dependent. And so now let's consider what that EMF has to be. To find this, we're going to use Faraday's law. So Faraday's law says that the EMF generated is equal to minus the time derivative of the flux. In other words, we're going to have to take the negative time derivative of this expression. So let's do it. So this is going to be equal to minus the time derivative of this. So I'm going to pull out all the constants first. So mu naught over 2 pi h of natural log d plus b over d and I naught. These are all constants. And now we're going to differentiate. So I write d dt of e to the minus at. So I'm just going to copy paste all these constants so I don't bore you by writing them. But the derivative of this expression is just going to be, so I'll write it here, it's going to be equal to minus a e to the minus at. And so I'll just paste this here. When I evaluate the derivative, I'm going to get minus a e to the minus at. This negative sign is going to cancel out with the one over here. So that disappears. And now we get this expression. And this is our expression for our EMF right here. And we can still see that it's time dependent. The exponential hasn't gone away. So that's important to note. Great. So now that we have that, we're asked to find the direction of the current in the rectangular loop. So to do that, let's consider our diagram. So actually, I'm just gonna, I think I'll go here. So we determined before that the magnetic field was going into the page. And now we know that the current is exponentially decreasing, right? Because it's a negative exponential. And so what we can say is, at time equals 0, we're going to have a maximum current and therefore a maximum magnetic field. A maximum magnetic field pointing into the page. And so over time, we're going to get a decrease in current and therefore a decrease in magnetic field. So you can imagine that over time, some of these excess will disappear. The loop doesn't like that. It wants to oppose that change. And so to oppose the decrease in excess, it's going to want to add its own excess. In other words, it's going to want to point its magnetic moment into the page. That's really important. So hopefully you can see that the decrease in magnetic field leads to a magnetic moment that points into the page. And so we're just going to point our thumb into the page. So grab your right hand, point into the page, and you should see that if you curl your fingers, you're going to get a clockwise current. So in other words, our current is going to be clockwise. And yeah, that's pretty much the problem. If you are able to do both problems that we just covered, you should be pretty set with Faraday's law. Of course, you should probably do a few more practice problems just in case, but these test pretty well the way you set up integrals and the way you sort of conceptually understand how flux works and current. So I hope that this was helpful. Let me know if you have any questions, and thank you for watching. See you soon, I guess. Bye. Thank you.